So, up to image processing will be the syllabus for whatever I will be covering till maybe another 2 lectures, right, that will come. And then whatever we will be covering or will start on biometrics, that will come in the final. In the last class, I was discussing about the edge detection, and we discussed different types of edge detection algorithm. One of them was Prewitt, right, Sobel, Roberts, and also we mentioned there are certain issues in front of you while writing the edge detection algorithms. The problem is that you have to decide a threshold in such a way, because you will be using the gradient, magnitude and direction, but sometimes what happens due to some reasons that your threshold is not catching or will not be able to catch the edge, because if you make the threshold is very less, then you may find that too many false edges are coming, but if you make the threshold is very high, then there are certain genuine edges you will be missing. So, because of various reasons, you may find that some part of the edges are very weak and your threshold is not able to detect those edges. So, you have to be very careful while detecting the threshold, that is the issue. Now, that edge detector, whatever you are using, they are using only one threshold value, right, and if it is exceeding that value, gradient magnitude along the direction, if you find it is exceeding the threshold value, you tell it is a edge point, otherwise it is not, and set of those points which are contiguous, you will tell that this is an edge or true edge, right. So, you observe, I do not know whether it is visible. See, in this image, this is the Sobel operator's output, and you will find that there are several edges here which are not connected, just it has broken. There is no link between the two edges, right. So, for example, this is I think this is visible for you. So, it is not connected, but it should have been connected. This is an edge, it should have been connected because of your threshold improper selection of threshold. This has come out like this. Now, once you design any edge detection algorithm, what are the things you are looking for? First one, you are looking that your algorithm must be able to detect the true edges as many as possible. This is the first condition, right. So, good detection, that means it must be able to detect all the true edges as far as possible. Second one is that good localization, that whatever way you are selecting the edge, it should be nearer to the true edge, because edge is like this and the true edge is that way, it should be nearer to that as far as possible. These are the two conditions you should look into while designing an edge detection algorithm, right. Now, by good detection, what we mean? We mean that you are minimizing the probability of false positive, that if whatever is the noise, it should not look like an edge, or you should not consider it as an edge. So, false positive should be as minimum as possible, and next one is that minimize the probability of false negative. That means that you should not tell a true edge as a not an edge, right. So, your threshold value should be such that this should be taken into account. Now, remember one thing, that they are inversely related, that if you want to make a very high threshold, yes, you will not be able to get the false edges, because you have given very high value of threshold, you will not be able to get the false edges, but at the same time some of the true edges also will be missing. Some of the true edges also will be missing, or if you give very low threshold, very low threshold, then what happens? Then you will be getting all edges, or says looks like an edge, all edges you will be considering in your system, and as a result some of the faults or some of the noises also you will be considering as an edge, and it will create problem. So, and one thing you remember that this it is very difficult to get a threshold, such a threshold which satisfies both of them, right. So, this is the important thing. So, this will create the two types of error also. We will discuss while we will be covering the biometric system, that what are the different types of error and how we should minimize it. Good localization, that means the detected edges must be as close as possible to the true edges. And another thing is that single response. What it means, that if this is a edge point, from there is a direction, obviously you will be getting the gradient direction and gradient magnitude, and towards the direction only you should get another local maxima. You should not get too many local maxima. Suppose this is an edge. Now, while I am looking for whether there is another, whether there is another neighboring pixel is an edge point or not, it should not give me several edge points, several local maxima, because if it gives you the several local maxima, so what will happen, that it will create an edge this way, it will create an edge this way and so on, and most probably that is not, generally it does not happen, because we assume the image is such that between the two neighboring pixel distance is not too much, right. So, symmetry is maintained. So, your threshold should be such that this type of scenario does not occur, right, and if it occurs, there should be a way out how to remove some of these false edges. For example, what we get, it's a vein pattern, right, because of if I take the vein pattern photographs or if scan image, you have the veins, it will look like this. It may look like this. This is your vein pattern here. Now, because of your here, because even though we are using the infrared camera, because of the here, you may find like this type of edges, you may find. Now, but these are not edges, it is a very easily, everybody will tell this is not edges, right, these are all false edges. So, that is the thing what we are looking for, that your threshold should be such that there are not too many local maxima around the true edge. What we have done in our case, that we have assumed that if it is this length of this edge is more than some number, then only we consider it is an edge, otherwise it is not. Now, Canny edge detector uses the true thresholds to detect the weak edge and the strong edge. That one is genuine edge, by if you put the higher threshold, they are genuine edge. If it anything, any gradient magnitude is greater than that threshold, it is an edge point. Another one is that I put the lower threshold and we check it is a probably an edge point, but we are not able to take the decision at this moment, right. And if it is less than that, the lower threshold, then it cannot be an edge point. Now, there are 4 stages of Canny's algorithm, because any algorithm for edge detection, we need to first remove the noise. So, same thing here also we have removed the noise. Second is that you need to compute, like Sobel and others, you need to know what is the intensity gradient of each pixel points. And third step is the non-maximum suppression. That is the thing what I am telling, that this part, non-maximum suppression. And once you have suppressed the non-maximum points, then use the image and hysteresis thresholding to determine the edges. Now, hysteresis thresholding is the major part what Canny has designed. Now, noise removal algorithm, here he has suggested that you use the Gaussian filtering algorithm. So, you raw image, you have just convolved with a Gaussian filter to get the noise removed image. Now, that image is used to estimate, to get the estimated intensity gradient of that image. Now, you remember the intensity gradient, we can use the Sobel operator, right, that to get one is horizontal direction, another one is vertical direction, and using this horizontal direction and vertical direction things, you can get the gradient magnitude and also you can get the direction. Am I right? Because you remember the direction, those things we have already covered, tan inverse of y by x, same thing. So, you know now gradient direction and also you know the magnitude, these two forms your estimated intensity gradient. And Canny has used both of them to determine whether a point is an edge point or not. So, you have now the gradient magnitude and gradient direction. So, non-maximum suppression, what it does, that he looks for a pixel, for each pixel, whether that gradient magnitude gives you the local maxima along the direction or not, right. Say you have a pixel point, what it looks, and you know the direction, gradient direction, say this way. So, he looks whether this point is a local maxima or not. That is the thing only he is looking. If it is, then he retains, otherwise he is throwing that no, it is not an edge point, right. That is the thing, he suppress if it is not a local maxima, and this obviously since he is suppressing, he will get some thin edges, right, but it is not a 0,1 value, it is a thin edges with some gradient magnitude values. We will show you how to compute later on. Now, see, the issue is, first problem we are facing the noise suppression by your filtering technique. Now, you remember that in the case of Gaussian filtering technique, sigma plays a major role. That you remember that a larger value of sigma, it becomes the mean filtering. So, but if you put larger value of sigma, right, or your mass size will be increased. Once you are increasing the mass size, you are reducing the noise, no problem, because it is coming to the smoothing effect and everything. So, you will get the, you will reduce the noise, there is no problem. But problem will come out that localization, edge localization problem, that it will worsen the edge localization. See, for this example, if you see, this is the very smaller mask you have taken and it is looking the same image with edges only, but too many false things are also there. But if I use a larger mask, it has suppressed several things and some of the edge lines, see these edge lines, they have been not in perfect way, perfect position, it has been deviated. So, localization will be a problem. So, you have to select your sigma in such a way, it should not be small and at the same time it should not be very large. This is the effect of low threshold and high threshold. If you put the low threshold, you see some of the Noise also you are visible, they are visible, you are not getting exactly whole edge, proper edges, but if you put the high threshold, only the boundary you can see, rest you cannot see. The next example is that this is the through edge detection algorithm you got this image, but you see that they are not linked. They should be, so you need the linking operator to link the edges, broken edges. Now, we have already mentioned that if you have the large threshold, you will be getting the true edges, and if you take the small threshold value, then it will give you some false edges also. So, these none of them is suitable for, if you use only one threshold value, will not give you the correct edge map. So, what Canny is suggesting, that Canny has suggested that you use two threshold, one is low threshold, another one high threshold. Now, what happens? First you use high threshold, you will be getting the true edges, right? These are genuine edges, there is no, but as you make it like this, you will get this type of edges, but they will not be connected. Of course, see now you traverse that edge, you make use of this contour of this edge, and you use now here the lower threshold based edge map, and you look for whether there exists any weak edge towards the direction, towards this direction. So, what I am looking that in this direction there is whether there exists any weak edge or not. If it is there exists some weak edge, you consider that weak edge, but you remember that you have to follow the direction, right? In that direction whether there exists any weak edge or not, weak edge you will be getting through the lower threshold one, small threshold value, and if there exists some weak edge towards that direction, you consider this is an edge, right. By that process you will be able to generate the good edge map. So, this is an original image, this is a gradient magnitude. Now, if we put some threshold, then the image looks like this, then the non-maximum suppression things. Here there is a line is that the direction vector has to be taken into account for seeing the local maxima. So, this is an example. Suppose that your direction is this way. So, what I am looking for, that if magnitude of ij is less than magnitude of this or magnitude of this less than this, then you set it 0, otherwise you consider it is an edge point. But it looks simple when your gradient direction is vertical or horizontal, right. But what happens if it is of this type? You have gradient direction, you have P and here R, and you are looking for Q, right. So, their complexity is increasing, because direction is not either vertically or horizontally. So, you need to know the interpolated value, you need to know the interpolated value of in between things, and then only you will be able to take the decision, right. Now, how to get it is not required to consider the bilinear interpolation, because line will be, if you think this way, the line will go this way, right. Then you need either this side or this side, horizontal or vertical, but you do not have to go the center of this point. Bilinear interpolation is not required, it is not that difficult, but a complicated one, just one directional interpolated value you have to check, and then you take the decision whether it is it should be set 0 or it should be retained. Now, standard thresholding technique is like that. If you get the difference operator, right, if you remember the reverse or inverted delta is the difference operator, which is nothing but f of x plus 1 y of plus 1 minus f of x y, right. That is the thing. So, if difference value, the difference of this value, if you define that it is greater than t, then you tell that this is an H point. So, you tell that Exy is 1, otherwise it is set to 0, right. So, through that you can get only the strong edges, or you can get strong edges in also the weak edges. So, there is no guarantee of continuity if the t is very high, because you will be considering only the strong edges. So, there will be discontinuity between the two sub edges. But in case of Canny, what do we have? One low threshold value, another high threshold value. Generally, high threshold value is almost equals to twice of the low threshold value. If you use, then the difference operator, if you get greater than the high threshold value, you will get 100% that true edges, and because they are strong edges. If it is less than the low threshold value, then it cannot be an edge point, but if it is lying between the low threshold value and high threshold value, then it may be an edge point or may not be an edge point, right. Now, these may be edge point, you will be deciding based on the neighboring pixels intensity gradient value magnitude and the direction. So, this is the thing that it is a high true thing, this is the weak edges, and you have to connect them, that is the idea. Now, if I think this is the algorithm, yes. So, if I define it algorithmically, I have the two edge map you have. One is with the high thresholded image, another one is low thresholded image. So, you have I1 and I2. Let us assume that I1 is the high thresholded image and I2 is the low thresholded image. Now, link the edges in I2ij into the contour, look in I1 ij, this is the low threshold value when gap is found. If there is no gap, it is anywhere true edge, you do not have to do anything. If gap is found, yes, there is a I2 ij is 0 there, then you examine the 8 neighbors of I1 ij, whether there exists a weak edge or not, whether there exists a non-zero value or not. If it exists, then you consider I2 ij as an edge pixel, right. However, there is a possibility that if there is a large gap, you may not be able to connect them, because after some time there is a large gap between two true edge. So, connecting is sometimes will become very difficult, because you may get several weak edges. Now, there is no guarantee that you will be following a path which will touch this one, right, because you may start going this way, which will lead to some other place. You may start following this path, which will take some other place, it will not come here. If there is a long gap between the two strong sub edges, connectivity may create problem, it may not get the connected one. So, this is overall algorithm. First smoothing, the differential operator you have taken, then you have considered non-maximum, and finally hysteresis thresholding. So, that one is the Sobel, and see that a Sobel, it looks very neat and clean, but lot of edge breaks are there, but it is not the case with the Canny. But you will find that Canny is one contains lot many edges compared to any other. This is the parrots one. So, you see that this will give you the better one. So, this a lot of broken edges are there, but this is not the case with the Canny. I think that is the, this is another example. So, this is all about your Canny edge detection or edge detection algorithms. Now, next one is the Fourier transform. How many of you know Fourier transform? So, these terminologies are known to you. Let us start from the scratch. A complex number x is of the form x equals to a plus jb, j is square root of minus 1 and a is the real part and b is the imaginary part, right. And you know that addition of the two complex number is also a complex number. Similarly, is the case with the multiplication. Now, there is a term magnitude and phase representation. Magnitude is nothing but square root of a square plus b square and phase is tan inverse of b minus a, and phase magnitude notation is absolute value of x e to the power j phi x, right. Now, if I write multiplication using the two magnitude phase representation x y, I can obtain absolute magnitude of x dot magnitude of y e to the power j phi x plus phi y. And complex conjugate x star is a minus j b, properties are x absolute value of x equals to or magnitude of x equals to magnitude of x star, and phi x is equals to minus phi x star, and x star is absolute value of square of absolute value of x. This is the Euler formula. E to the power plus minus j theta is equals to cos theta plus minus j sin theta. This properties holds good, very simple properties. And now, sine function and cosine function, they are periodic functions. A general form of sine and cosine functions are a, which is amplitude sine a t b t plus b, t is time domain things time and b is the what phase shift, and 2 pi by absolute value of a gives you the period. This is the well known sine and cosine function for different values of a and a. Shifting, if you can shift by a constant b, phase shift, right, and you can tell, see from this also you can draw the conclusion cosine is a shifted sine function. Changing of amplitude, right, just you put the value capital A by 3, you will be getting this type of graph. Changing the period is I told you that t is nothing but 2 pi by absolute value of a, and consider a equals to 1, b equals to 0 and y is equals to cos of a t. A if you consider 4, period becomes pi by 2, and you observe that it has become the shorter period and higher frequency, so it becomes the faster oscillation, and frequency becomes 1 is defined by 1 by t. So, sine of a t can be expressed as sine of 2 pi f t, if f is the frequency. So, image transform. So, sometimes you know what happens that you want to perform any operations on image, it becomes very difficult or it is not, you are not able to visualize the things. Well, what do we do? That we convert or transform from the spatial domain to another domain, perform the operation on that domain, and then they take the inverse of the transformation. That is the thing. So, first is the transform the image into another domain, then carry out what operation you want to perform, then perform again inverse transformation on it. So, f x y was your originally pixel value of a image, and this is the forward transformation, and the resultant you get the forward transform image, and inverse one is just it is inverse of it. Now, the kernel is said to be separable. If you can write r x y u v, that is the kernel, you can write r 1 x u dot r 2 y v. Now, r 1 x 1 is along the x axis you can have some kernel, and along the y axis you can have another kernel. Kernel is said to be symmetric if you can write R1 Rxy u v equals to R1 xu dot R1 yv. Now, these are the common terminology we will be using in our discussion. One is that Fourier transform. Generally, we do not write CFT, we write FT, and then discrete Fourier transform, because we will be performing the operation on discrete domain, and then first Fourier transform. But we will not be discussing the algorithm how to do, because these are all available. Just I want to browse the things, so that while discussing the algorithms in biometric system, you should think that yes, this is the thing we have done. Fourier series theorem is like any periodic function can be expressed as the summation of or infinite summation of with respect to the cosine function and sine function, which is defined by f t equals to a 0 summation n equals to 1 to infinity a n cos n f 0 t plus summation n equals 1 to infinity b n sine n f 0 t, where f 0 is called the fundamental frequency. This is one example, the sum of some functions you can get 1 FTS. So, continuous Fourier transform, this transform a function from the spatial domain to the frequency domain, and this is the f f x is equals to f u equals to minus infinity to plus infinity f x e to the power minus j 2 pi u x, where e to the power plus minus j theta is defined by cos theta plus minus j sin theta. Similarly, inverse is defined. So, the low frequency corresponds to that it is continuity of the intensity level. That means, there is no change, or gradually it is changing the intensity value, right. But high frequency corresponding to the sudden change, or you can get the age information there. So, suppose we want to do the filtering operations on it, then take the Fourier transform, and then you perform some operations to remove the undesired component, and then you just take the inverse of it, you will be getting back your original image. Now, f u is a complex function. So, f u can be expressed as r u plus j I u, and magnitude is defined by square root of r u square plus I square u, and phase is nothing but phi f u is equal to tan inverse I u by r u, and magnitude phase representation is magnitude of f u e to the power j phi u, and power of f x also r square u plus I square u. These are the two functions defined, rect x and sin c x, and delta function is defined. I think that is the thing important, right. Delta function is defined by delta x equals to limit a tends to 0 1 by a rect x by a. This is the functions, and properties is minus infinity plus infinity delta x f dx is equals to 1, and shifting thing is that minus infinity plus infinity f x delta x minus x 0 dx equals to f x 0. So, Fourier transform of delta function is given by minus infinity to plus infinity delta x e to the power j 2 pi u x dx. This result gives you the e to the power 0, which is 1. So, this is a simple shifting properties. It maintains the this is a f of x minus x 0. You will be getting is its corresponding transformation will be given that e to the power j 2 pi u x 0 f u. Then Fourier transform of the cosine function and also sine function are also given. This also you can easily find, because just you have to browse your book, you will be able to get it. This are I do not want to cover this thing. Fourier transform in 2 dimension is that obviously minus there will be 2 integration f of u and v, and so you will be getting this, and inverse of this f inverse f of u v is equals to f x y minus infinity plus infinity minus infinity plus infinity f of u v e to the power j per 2 pi u x v x du dv. Now, the question is given that was the on continuous domain, it is difficult to, it will not be possible for us to use them. We have to go to the go to our in our discrete domain. There is one slight problem. Anyway, fx equals to, so I have divided into the, as you know you do in the case of numerical methods, same things, fx equals to f of x plus x0 plus, this is not x, this is some other I, let us consider I delta x, and I is 0, 1, 2 n minus 1. So, I partition them and then I get these values. It should not be x delta x, it should be I delta x. And forward DFT formula is f of u 1 by n summation f of x, this is a one dimensional things, e to the power minus j 2 pi u x by n, and inverse is coming summation over u equals to 0 to n minus 1 f of u e to the power j 2 pi u x by n. This should be again I delta u, and delta u is equals to 1 by n delta x. So, in the case of two dimensional fxy is m cross n, if you assume then f of u v becomes 1 by mn, and you have the same formula. Only thing is that the two dimension, it considers the two dimensional effect, and inverse is equals to summation over u equals to 0 to m minus 1 v equals to 0 to n minus 1 capital F u v e to the power 2 pi u x by m and v y by n. Now, if m equals to n, the formula becomes very simplified one, just I put m equals to n, nothing else. Now, if you visualize that f of u v, you observe that range domain for this image becomes very, very large. Now, if you use some scaling factor on it, then you can realize the effect. Now, the certain properties that 2D DFT can be computed using 1D DFT. Say you have f of u v is equals to 1 by n summation over x 0 to n minus 1, y 0 to n minus 1, f of x y e to the power minus 2 pi x u x plus v y by n, and inverse is also correspondingly written. Now, you know this one can be expressed as this into this, the product of the two e functions. If it is the case, so we can rewrite your f of u v as the product of the two components. Now, let us assume that this is equals to f of x v. Then f of u v is nothing but 1 by n summation over x equals to 0 to n minus 1 e to the power minus 2 j pi u x by n f of x v. So, you have summation y equals to 0 to n minus 1 f of x y e to the power minus j 2 pi v y by n, which can be written as n times of 1 by n summation over y is 0 to n minus 1 f x y e to the power j 2 pi v y by n. That means what? N times you will be doing the row wise DFT. N times you will be doing the DFT row wise of x y, and once you have done it, then 1 by n summation over e to the power j 2 pi u x by n f of x v, and that is only one time DFT you will be computing along the column wise. So, this is a separate important property it obeys, and as a result you can have the very good or first algorithms to design or to obtain the value of discrete Fourier transform. Now, DFT and its inverse are periodic with a period of n. That property also you can easily visualize f of u v equals to f of u plus 1 n v, and if f of u v plus n or equivalent to f of u plus n v plus n. It obeys the property of symmetry. We have already defined what is the symmetry property, and f of x y, if it is real, then f of u v you can easily show that f star minus u minus v, and which indicates that magnitude of f of u v is equals to magnitude of f of u minus u minus v. If further you can see that f of x I, if it is a real and even, then f of capital F of x u v is also real and even. Similarly, is the case with odd. Oh, f of u v is imaginary or odd. So, this is translation is an important property in DFT. See, in the translation in the special domain f of x minus x 0 y minus y 0, you will be getting f of u v e to the power minus j 2 pi. Just you put the value in your original algorithm, then you will find that some part of e to the power will be there, that you can is a constant because it is an u 0 and v 0. So, you can take out x 0 and y 0. So, you can take out. So, if you can do it, the reverse one, inverse one also will be the same, satisfying the same property. You have f of x y, you multiply this, you will find the it is a formula for capital F u minus x u minus u 0 and v minus v 0. Now, to show a full period, you need to translate the origin of the transform at n by 2. This is the full period, that n by minus n by 2 plus n by 2. Now, if you want to show the full period after shifting, right, of transform, then you need to show the full period. So, that means you have to shift from n by 2 to n by 2. So, minus n by 2 to n by 2, that is the thing. So, you need to shift from minus n by 2 n by 2, here it is 0 to n minus 1. So, that shifting is required, that means u will be n by 2 and v will be n by 2, that has to be u 0 and v, instead of v 0 you have to put that. So, to move f of u v at n by 2, n by 2, so you will be taking u 0 equals to v 0 equals to n by 2. So, using f of x y e to the power 2 j 2 pi u 0 x plus v 0 v y by n, and is a transform is f of u minus u 0 v minus v 0. Now, if you consider this part, right, and u 0 you put n by 2, v 0 you put n by 2, and then you are getting that it is nothing but e to the power j pi x plus y, which is nothing but minus 1 to the power x plus y. So, basically you have f of x it minus 1 to the power x plus y is nothing but f of u minus n by 2 and v minus n by 2. So, that is a sort of translation property. And now, rotation. So, rotating f x by theta rotates also f u v by theta. So, addition and multiplications on DFT, that if you add the two DFT, it resultant is also DFT, and but it does not hold good in the case of multiplication. Scaling is the another one. F of x y is equals to in the transformer is a into f of u v, that is also a is a scaling factor. If it is very straightforward, if you can put in the formula, you will be easily getting it. So, finally, you have the property of average. F of x y is equals to 1 by f of x, average of f of x I or f bar x y is equals to 1 by n square summation over x 0 to n minus 1 y 0 to n minus 1 f of x y. Now, what happens that if I put u is 0 and v is 0. So, this becomes 1, right. So, it becomes 1 by n summation f of 0 0 is 1 by n summation x equals to 0 to n minus 1 0 to y is 0 to n minus 1 f of x y, right. And so, that is the thing that f 0 0 is equals to 1 by n summation over 0 to n minus 1 0 to n minus 1 f of x y. Now, if you compare these two, what you get, that f bar x y is nothing but 1 by n of f 0 0. So, that is the another property you get. So, these are the 8 properties you have on your DFT.